fit, that is, takes up the greater percent of area. A square peg in a round hole, which is shown here, or a round peg in a square hole, which is shown here. Okay, so I redid the drawing, and the first thing I did was to go ahead and create a 45-degree angle by drawing in my radii here and dropping this perpendicular line. These angles start out as 90 degrees because we're dealing with a square, and if you bring that radius in, it's going to bisect that angle, so you have a 45-degree, 45-degree right triangle. Our goal is to find this length because we're trying to find the entire length of the square. That will allow us to then get the area of the square. Okay, now I'd like to quickly review 45-degree triangles with you. You may recall that this is the ratio, 1, 1, square root of 2. This, of course, is the hypotenuse. It's the longest length in this 45, 45 right triangle. These two are shorter lengths. So let's go down here and do some examples. The key is the square root of 2. This is the factor that's going to help you find your lengths. Okay, so let's look here on the upper left. We're given the hypotenuse. The hypotenuse is the longest limb of the triangle. These are shorter. Therefore, we divide by the square root of 2. When you divide by square root of 2, you are going to have a shorter length than the 5. Here, on the upper right, we're given the shorter length. When we move from the shorter length to the hypotenuse, because the hypotenuse is longer, we're going to multiply by the square root of 2, and that will be the length of the hypotenuse. So again, down below, we're given the hypotenuse. To get the shorter side, we divide by the square root of 2. Here, we're given the shorter side. To get to the hypotenuse, we multiply by the square root of 2. So we are going to do the same thing with our problem here. Okay, we're given the r value. The r value is the hypotenuse of this 45-degree right triangle. We need to find this shorter side. Therefore, we're going to divide by the square root of 2. And this length is going to be r divided by the square root of 2. Since we have two of these lengths, our length of this square is going to be r times the square root of 2, or excuse me, r over the square root of 2 plus r over the square root of 2, or 2r over the square root of 2. Now I could simplify that, but I don't need to because I know in 2 seconds I'm going to be multiplying the two sides, and that radical in the denominator is going to go away. So we have the area of the circle is simple, that's just pi r squared. And now to find the area of the square, we multiply side times side. 2r times 2r is 4r squared. In the denominator, we are squaring a square root. So eventually, we are just going to get the radicand, which is what's inside the square root. Here's the algebra behind that. I changed the radical 2 to 2 to the 1/2 power. Then I use the power rule. 2 times 1/2 gives you 1. And 2 to the first power is just 2. And this 2 and this 4 cancel out and leave 2r squared for the area of the square. So now we have the area of the square. We have the area of the circle. Now the problem asks us, here's another way we could have done it. Rather than create the 45-degree triangles as I just showed you, we could have just extended this r as a diameter and then use the Pythagorean theorem. Okay, so here's our right triangle. There's the hypotenuse, which consists of 2r. Our goal is to find the s here, and we just use the Pythagorean theorem. So the hypotenuse squared, which is 2r, equals the two sides, the sum of the two sides squared. If we simplify, we get 4r squared equals 2s squared. Further simplify, then we take the square root of both sides. We are dealing with lengths, so we can drop out this minus version of the square root. We don't need that. And as we further simplify, we pull out the square root of 2. We keep the square root of the r squared because we know that's going to simplify to r. And our final side is going to be r times the square root of 2. So if we have the square, and each side is going to be the square root of 2 times r, then we know the area of the square is going to be this side squared. And we have the square root of 2 times r squared. Again, we're going to use the power rule. The radical 2 squared is here, and this is r squared. I change the radical 2 to 1/2 power. Again, use the power rule. That becomes 2r squared. So we got the same answer doing it in a slightly different way. Okay, so they ask us how much of the circle's area does the square take up? Or what percentage of the circle's area is covered by the square? So I redrew this little small version. Okay, we have this area of the square. The question is, how much of the circle's area does it cover? So we put the area of the circle in the denominator, the area of the square in the numerator, and we multiply by 100. That gives us the percentage of the circle's area that is covered up by the square. If the area of the square completely fit into the circle, then these two numbers would be equal. We would get 1, and we would have 100% of the circle being covered up. But we know that's not the case here. We know that only a portion of the circle is covered up by the square. So let's insert the values that we got earlier. Here's the area of the square. Here's the area of the circle. When you simplify, these r squares cancel out. If you substitute 3.14 for pi, you get 0.637 times 100, and you get about 64%. Okay, let's now move to part 2 of the problem. We look at this scenario, where we now have a circle inside of a square. This problem is much easier. The sides of the square are going to be shown here. There's a radius, here's another radius. So the side of the square is going to be 2r. 2r times 2r for the area of the square will be 4r squared. The area of the circle, again, is pi r squared. So we ask ourselves the same question. What percent of the entire square's area is covered up by the area of the circle? So again, we put the area of the square in the denominator, and we ask ourselves what percentage of this is covered by the area of the circle. Here's our area of the circle. Here's our area of the square. We simplify. We get pi over 4, and if we substitute 3.14 for pi, we end up getting approximately 78.5%. Therefore, the answer to our question here, this square is going to cover up only 64% of the circle's area. Here, when we have the circle inside the square, it's going to cover up a more significant portion of this square's area. As a result, this is considered the better fit.